recently upgraded my CPU cooler from the stock Ryzen 5 3600 cooler to this much bigger and beefier Fantex cooler. Not sponsored at all by Fantex, but if you are looking to get a nice air cooler for your CPU, I'd recommend checking this one out. Either way, here is the CPU cooler in the actual PC. It was an incredibly tight fit, and there's only a couple millimeters between the top of these fans and the glass, and as many of the reviews say, I had to move this fan where it was originally in front here, but it has a conflict with the RAM there, so I just moved it there to the back, and it works perfectly fine. But now that I have upgraded this one last component, well, I guess second to last component, it left a very obvious and glaring problem with the computer, and that was this gross little toilet paper tube that I was using as a GPU support. And while I can't even see inside of my computer because it's underneath my desk, turned away from my chair, tucked into a little corner, it's the thought behind having this gross little cardboard tube in this computer that I built and designed myself, and I had carefully color coded everything so it matched the same white and black aesthetic. And so decided, have a 3D printer, why don't I go ahead and 3D print a little GPU support that would act much like the cardboard tube and basically just keep the GPU from tilting over and stressing the motherboard back here. And I thought, while I was making that GPU support, I've got this nice big beefy CPU cooler now. I can probably have a little less air going to my CPU, and I can instead have some more air going to my GPU because it was overheating a little bit in the past. And so I thought, how about I make a little divider going from the top of the second fan here to the front bottom edge of the GPU, just so I can divert some of the air that would be used to go over top of the GPU and instead divert that underneath the GPU where it would be sucked into its cooling fans and in turn create greater cooling for the GPU and in turn greater performance because it has that cooling so it doesn't have to work as hot. And so I went ahead and measured out the dimensions of the computer case and started building in SolidWorks. The first step in SolidWorks was to create a simple model so I can test various airfoil designs. This is done by just going into the computer case and taking some basic measurements like the height between the bottom of the GPU and the top of the power supply shroud, the gap between the power supply shroud and the back of the fans. You got the width of two of the fans plus a little gap on the bottom, the gap between the front of the GPU and the back of the fans, and then just a basic sweep for various airfoil designs. I would iterate on this sweep right here by these three lines to check different shapes and sizes to see what sort of impacts they had on the actual airflow underneath the GPU card. Once I had created this shape, I would simply do a little boss extrude that would go the width of the computer case, and I had the basic model to run my tests on. Unfortunately, I don't have SolidWorks simulation, so I couldn't just do the simulation in SolidWorks, but it's easy enough to load it into SimScale, which is a website, and do the test through there. And so with that, I'll head on to SimScale. So here we are in SimScale. As I said just now, this is a website, but to be a little more specific, it is a cloud-based finite element method simulation software website. I've only ever used it to do computational fluid dynamics, but you can run a bunch of other different types of simulations if you so desire. Best part about it, it's free up to 3,000 core hours. I used maybe 3 core hours on this project, so I will not be running into that limit anytime soon. And it's also super easy to import geometries from other sorts of softwares. As you can see here, you don't need to save it as anything special. You can simply save it as the native geometry or native part file that would be in your CAD software and import it directly into SimScale. As you can see here, I have imported the part I made in SolidWorks there. And so I specify this is all going to be air. Initial conditions, it's all basic conditions of basic pressure, basic temperature, nothing too fancy. And then I specify the boundary conditions. And so on this front face here, this is where the wind from the fans will be blowing in. I give it a value of -10 meters per second, which I thought was fairly typical, thought it was a good number to go for a fan, and it's -10 just because the X is in the positive direction, and so negative will be blowing back into the shape. I then specify the walls that the air will be bumping up against, so that's everything but this front face and this back face. This will be the sections where it has the boundary layers, and I'll have to do a little more simulation. And then finally there is the outlet. I specified there is a pressure outlet here with 0 gauge pressure. It's going to be atmospheric pressure here because there isn't going to be a fan or anything sucking out. Technically, I guess there is the fans pulling up, but for simplification, I just said there's 0 pressure on this side, and so all the wind will just blow straight through the shape. And then work, do the numerics, do the simulation controls. These are fairly important, and we'll specify sometimes you'll run it and it will take too long for the simulation, because on that basic simulation package you can only go up to, I want to say, an hour of simulation time, and so sometimes you'll have to adjust these to make sure you don't cross that time, otherwise your simulation won't run. You then mesh it, and you can see, if you've ever seen CFD or finite element methods, basically breaks your shape down into a series of nodes and elements connecting those nodes. And there is specifically more complicated node sections around the edges, because that's where the more complicated math will have to be, and it'll have to be more accurate along those areas where there is that boundary layer. Once you've done that, you can then run a simulation. If I run a simulation right now, I will not run a simulation, but it'll take, you can see here, this one took 13 minutes, took about 0.43 core hours, so maybe a little bit over the 3 hours total, but still plenty of time in that 3000 core hour limit. And so I'll go to the one, I did a bunch of different iterations with different shapes. I'll talk more about these shapes in a second, but I'll just show you the shape that I showed in SolidWorks and showed in this preview here. So we'll load up the solution field for that. As you can see here, we have a nice cross angle view of the cutaway. Right now I'm just looking at the velocity magnitude. I can choose a bunch of different velocities. I can do in the X direction, Y direction, Z direction. I chose the magnitude because that'll be kind of a better idea of the overall speed of the velocity. And as you can see here, it's kind of slow along the front face, nice even speed, and then slowly speeds up as it approaches the tightest section, and then you see a speedy section along the top here with a much slower section along the bottom there. If I then instead look for the pressure, which is one of the two things I'm looking for, I want to make sure we have good velocity through the airfoil and through the gap, because that'll mean more air flowing through it. And I want to make sure the pressure isn't too high along this front face, because that'll mean it'll be fighting to head back through the fans, which is not what I want. I want all the air to be going underneath the GPU here. And so as you can see on this basic one, you have a high pressure spot in the bottom and another high pressure spot at the top. makes sense. This is where the air is really constrained as it's pushed by the fans up against this face. Can't go down, can't go forward, all of it has to go up. So there's a super high pressure section right there. The same to a lesser degree up at the top there. And then it heads into lower pressures as it reaches here. As it isn't constricted up against those faces, it can just flow straight through the section, straight out this outlet here. And so I'll show you a collection of the different tests that I did. Here's a nice little Google Docs collage of the various pressure maps on the top and velocity and magnitude maps on the bottom. Unfortunately, these pressure maps kind of turned out to be a little useless. Would have been somewhat useful if all of these colors specify like a specific pressure, but they're all relative to each of their pressure maps, with the dark red being the greatest pressure. And so, like say on this one here, where you'd think, oh, it's only a light orange on the bottom there, it's not too bad, where in reality, it's just that the dark red is at this very tippy top, and so it's still about the same pressure all along these bottoms as the max pressure, it just isn't the same color. The velocity magnitude maps, on the other hand, just look very helpful and were quite informative. The biggest difference among all of them, as you can clearly see, is when I just had a straight corner on this bottom side. There's no fillet or curve along there to help direct the flow along the top, and that caused the velocity magnitude to increase in this kind of section that's going down to the bottom right, as opposed to having a nice kind of uniform cross section across this area, which having it like this leaves the slow section at the top corner and the same slow section at the bottom corner. But the slow section on the top is definitely something I'm going to look to avoid, because there's going to be an intake fan for the GPU right around here. And if there's no air blowing in that general direction, the GPU fan is obviously going to get a little less air than it perhaps should. Second interesting thing to note from these velocity magnitude maps is that when you had the curves at the top, you had a more uniform velocity profile as you went in the X direction, while once you got rid of that curve at the top and just did a sharp point, it's kind of more of a triangular shape to it, as it has to speed up much faster, doesn't have that kind of grace period as the curve generates into this bottom slope here. It just straight into the bottom slope, and so it has to automatically speed up a fair bit faster. But from these, I decided to go with kind of this design here, which was not a super long curve at the top and still has that little curve at the bottom. This helped balance out having, if you have this curve at the top be too long, you then get a vertical line like you would at the bottom. Like the longer that curve is, the less horizontal this line will be, the more vertical it will be. And I wanted to avoid that because obviously you're getting the choked air at the bottom here, where having a nice vertical line, it's not as choked. And then having this little curve at the bottom also helped keep the flow from diverting away from the fan and kept it up nice and tight along the top. And here we have the incomplete version 1 design of the graphics card support. As you can see, it has a nice airfoil running down the middle of it, nice and smooth, just like the test profiles. Also have 2 flaps on either side of the airfoil. This is supposed to help the air stay actually on the airfoil and flow down it, as opposed to just flowing around it and making the airfoil useless. Also started working on designing a section that allows for the height of the graphics card support to be adjusted. This is simply design philosophy I like to follow, where you create something that has adjustability in it, so you have a bit of play when you're making it, and you can have a bit of flexibility in case stuff doesn't line up as it perhaps should. Unfortunately, it was getting kind of late when I realized that this design wasn't going to actually work and I was going to have to remake all of this. And so I just called it a night and decided I'd work on it again in the morning. So this is as far as this design actually went, but strangely enough, this was a bit of a blessing in disguise, and I'll talk about that a little bit later. As I was falling asleep that night, I thought back to all the design classes I had taken throughout university, and how the profs had always talked about how the further along a project is, the more expensive it becomes to fix that project if a problem arises. And so I thought, before I go and spend a ton of time in SOLIDWORKS remaking the airfoil design, and before I spend a ton of time in Filament 3D printing that airfoil design, why don't I make a very basic model of it, just out of some cardboard and some masking tape, just to see if the design actually has merit. You may notice that this bottom corner here does have that kind of sharp angle I wanted to avoid from the simulations, but I figured it wouldn't be too big of a deal, too much of a difference just for this initial test. And I also figured, unlike in the simulations, there will be a fan right here, right where that kind of dead spot was, and that would help suck in the air and eliminate that dead spot. And so I went ahead and ran some tests. For these tests, I used the Superposition Benchmark software along with Hardware Info 64 so I can measure the temperatures of the various components of my gaming rig. This is a very beautiful benchmark to run, and I figured I'd let you see some of the benchmark running on the high setting. I ended up running the benchmark 4 times so I can compare the base case to the support case for both 1080p Extreme and 1080p High. As you can see by the colored boxes, these results weren't very favorable to having that support in place. Across the board, I saw my overall FPS drop, as well as the corresponding benchmark score, and I saw the temperatures of my CPU die rise as well. Interestingly enough, the support did seem to do its job in reducing the GPU temperatures, but seeing as these temperatures are still reasonably high for having 100% GPU usage, and my score went down and the FPS went down, this slight reduction in temperature did not seem worth it. And so that's where the lesson comes in. It's one thing to learn it in class and a whole nother thing to actually learn it in person. It is definitely a good thing to try and test stuff as soon and early into the process as you can, because as you can see here, I nearly went ahead and spent a ton of time in SOLIDWORKS and a ton of printer filament and a ton of printer time to print out a GPU support, and it very likely wouldn't have worked at all, and it would have just been a complete failure and waste of my time. And so I'm very glad I went ahead and did this test, and I'll definitely be looking for ways to do tests similar to this and use math to test problems and test solutions before I go ahead and actually create them in the future. So here is what I actually ended up printing. Much sleeker, much more smaller design than the original massive airfoil. I have Aprolod written on the front to represent the brand. Then a nice mixture of straight lines and curved lines for a bit of artistic flair. Got a bit of a cutout in the back here because I figured I get rid of that support material, save a bit of filament, and just have these two pieces on the side to help support the piece from bending. And then I have two little cutouts in the top and the bottom, so I can throw some gym matting in there to give it a bit of friction so it doesn't just slide out underneath the graphics card. Hardest part of this was probably cutting all these letters in, because I guess SolidWorks, at least my version of SolidWorks, doesn't have a way for you to just draw a line and have the letters be kind of in the middle of the line. Well, they can be in the middle of the line, but they can't be 90 degrees to the line. They have to be flat on top of the line like this. And so I had to go ahead and do a big linear pattern to get these all nicely spaced out. But in the end, they are nicely spaced out, and I think it looks quite nice. Here it is on top of my desk, looking nice and finished. Printer turned out quite well, and letters perhaps should have been a little bit bigger than they are, but the line down the middle still held everything nicely in place, and so it worked out well. And then here it is inside of the actual computer, sporting the graphics card nicely, and looks a million times better than that old cardboard tube did. And so, thank you very much for watching, and I hope you'll catch me in the next vid when I talk about a longboard braking system I've been working on.